Instantaneous velocity. The average velocity tells us how fast an object has been moving over a given time interval but does not tell us how fast it moves at different instants of time during that interval. For this, we define instantaneous velocity or simply velocity, v, at an instant, t. The velocity at an instant is defined as the limit of the average velocity as the time interval delta, t, becomes infinitesimally small versus equals dx, dt, and it is the differential coefficient of x with respect to t. It is the rate of change of position with respect to time at that instant. The graphical method for the determination of the instantaneous velocity is always not a convenient method. For this, we must carefully plot the position-time graph and calculate the value of average velocity as delta t becomes smaller and smaller. It is easier to calculate the value of velocity at different instants if we have data of positions at different instants or exact expression for the position as a function of time. Then, we calculate delta x divided by delta t from the data for decreasing the value of delta t, and find the limiting value. Note that for uniform motion, velocity is the same as the average velocity at all instants. Instantaneous speed or simply speed is the magnitude of velocity. It should be noted that though average speed over a finite interval of time is greater or equal to the magnitude of the average velocity, instantaneous speed at an instant is equal to the magnitude of the instantaneous velocity at that instant. The velocity of an object, in general, changes during its course of motion. How to describe this change? Should it be described as the rate of change in velocity with distance or with time? This was a problem even in Galileo's time. It was first thought that this change could be described by the rate of change of velocity with distance. But, through his studies of motion of freely falling objects and motion of objects on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant, it decreases with the increasing distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration, a bar over a time interval, is defined as the change of velocity divided by the time interval. A bar equals v2 minus v1 divided by t2 minus t1, which is equal to delta v divided by delta t, where v2 and v1 are the instantaneous velocities or simply velocities at time, t2 and t1 it is the average change of velocity per unit time. The SI unit of acceleration is meters per second square. On a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2, t2 and v1, t1. Instantaneous acceleration is defined in the same way as the instantaneous velocity. A equals to limit delta t tends to 0 equals to delta v divided by delta t, which is equal to the differential velocity divided by the differential time. The acceleration at an instant is the slope of the tangent to the v-t curve at that instant. Since velocity is a quantity having both magnitude and direction, a change in velocity may involve either or both of these factors. Acceleration, therefore, may result from a change in speed, magnitude, a change in direction, or changes in both. Like velocity, acceleration can also be positive, negative, or zero. The position-time graph curves upward for positive acceleration, downward for negative acceleration, and it is a straight line for zero acceleration. In case of constant acceleration, the average acceleration equals the constant value of acceleration during the interval. If the velocity of an object is v0 at t equals to 0, and v at time t, we have acceleration, a bar equals to v minus v0 divided by time t minus 0, or v equals to v0 plus acceleration, a into time t. An interesting feature of a velocity time graph for any moving object is that the area under the curve represents the displacement over a given time interval.
Uniformly accelerated motion is a fundamental concept in physics that describes the motion of an object when it experiences a constant acceleration. This concept is crucial for understanding various physical phenomena, from the motion of falling objects to vehicles accelerating on a highway. Several key equations relate displacement, time, initial velocity, final velocity, and acceleration, providing a comprehensive framework for analyzing such motion. The first equation to consider is V equals V0 plus at. In this equation, V represents the final velocity of the object. V0 is the initial velocity, A is the constant acceleration, and is the time taken for the motion. This equation establishes a direct relationship between the initial and final velocities of an object undergoing uniform acceleration. It indicates that the final velocity can be calculated by adding the product of acceleration and time to the initial velocity. Graphically, this relationship can be represented on a velocity-time graph. The slope of the graph represents acceleration, while the area under the curve corresponds to the displacement of the object. This graphical representation allows for a visual understanding of how an object's velocity changes over time and how that change translates into displacement. From this foundational equation, three essential equations can be derived, each providing unique insights into the motion of an object. The first is V equals V0 plus at, which we have already discussed. The second equation is X equals V0t plus half at squared. In this equation, X denotes the displacement of the object. This equation shows that displacement is influenced by both the initial velocity and the acceleration acting on the object over time. The term half at squared accounts for the additional distance traveled due to acceleration, emphasizing the role of time in the motion. The third equation, V squared equals V0 squared plus 2ax, illustrates the relationship between velocity and distance traveled. This equation is particularly useful when time is not known, or when analyzing scenarios where an object's velocity and displacement are of primary interest. It reveals how the square of the final velocity is related to the square of the initial velocity, the acceleration, and the displacement. This equation is often employed in various applications, such as calculating the stopping distance of a vehicle or determining the height reached by a projectile. Together, these equations provide a comprehensive understanding of how velocity and distance relate to time and how velocity varies with distance. They serve as the foundation for solving a wide range of problems in physics, from simple motion scenarios to more complex situations involving multiple forces and accelerations. When examining free fall, the concept of uniformly accelerated motion becomes even more significant. An object in free fall experiences a constant acceleration due to gravity, denoted as g, which is approximately 9.81 meters per second squared on Earth. To analyze the motion of an object in free fall, the time interval of motion can be divided into equal segments, represented as t. The distances traversed during these intervals can be calculated using the equation y equals half gt squared. This equation indicates that the distance fallen by an object is proportional to the square of the time elapsed. As time increases, the distance fallen increases significantly, illustrating the accelerating nature of free fall. By considering minus half gt squared as y0, the distances covered in successive seconds can be expressed in a simple ratio, 1.3, 5, 7, 9. This means that in the first second, an object falls a certain distance, and in the second second, it falls 3 times that distance, followed by 5 times in the third second, and so on. This remarkable finding was established by Galileo Galilei, who was the first to conduct quantitative studies of free fall. His experiments and observations laid the groundwork for classical mechanics and provided a deeper understanding of motion. Galileo's work emphasized the importance of empirical evidence and mathematical reasoning in the study of physics. He demonstrated that all objects, regardless of their mass, fall at the same rate in the absence of air resistance. This principle challenged the prevailing beliefs of his time and paved the way for future scientists to explore the laws of motion. Understanding these equations and their implications is essential for anyone studying physics. They not only enhance comprehension of motion, but also illustrate the profound insights of early scientists like Galileo, whose contributions continue to influence the study of physics today. The equations of uniformly accelerated motion serve as powerful tools for analyzing a wide range of physical scenarios, from everyday experiences to complex scientific inquiries. In conclusion, uniformly accelerated motion encompasses a set of fundamental equations that relate displacement, time, initial velocity, final velocity, and acceleration. The equations v equals v0 plus at, x equals v0 t plus half at squared, and v squared equals v0 squared plus 2ax provide a comprehensive framework for understanding motion. The study of free fall, as established by Galileo, further illustrates the principles of uniformly accelerated motion and highlights the importance of empirical research in the development of physics. These concepts remain vital for students and professionals alike, serving as the foundation for further exploration in the field.